introduced him for a talk, I was saying today's thesis defense will be by Jack because he was my student 11 years ago. But anyway, I'm very happy to introduce him today. We'll be talking on absolute boundedness of unicritical polynomials.
Thank you very much, Larry, for introduction. It's very, very special for me. So first of all, I would like to thank Professor Catalan and the organizers for organizing such a wonderful conference here. This is the 5th edition already, and second edition and the 3rd edition in 2018 and 19. HI and it's still going strong. And you saw that I'm gonna discuss today basically grew out from the thesis that I work with Professor Lawrence Washington, or as students we would call him Larry. Then I continue to focus on a specific problem here at the Sorbonne University with the help of Professor Washington, and also with the help of Professor Mark Hindry and Loic Murrell. Professor Loic Murrell was there at the time, so I was very fortunate to discuss this problem with all of them.
Maybe I want to ask once more whether the audible. Hello.
Can you still hear me, the audience online?
Yes, we can hear.
Okay, thank you very much.
It is. Let's take it out once. No, I think that would be uncomfortable.
Can you use that keyboard?
Yeah.
Yes, thank you very much. All right, so carry on. Now, let me remind of us about the system that we're gonna work on. It's gonna be very simple, at least in the beginning. So if we have a set, let's say set S and a map, that's all we need for doing dynamical system, or in this case, we're gonna call discrete dynamical system. So that means if we have a natural number n, we iterate n time as this. So we're gonna call this n iteration. And the set that we are interested in is the forward orbit. Say we start with the initial point Z in S, then the set of all forward orbit Z, the f of C, second iteration of Z, so on and so forth, is called a forward orbit. Now, the question is, when is this set finite? Of course, if the set S itself is finite, it's going to be finite already. But if S is not, then something interesting happens. And for the point S, the Z in S, that come back to itself after k iteration, this is called period. And the minimum number k is called the period of minimum period of the Z under F, or we can call exact period. And the set of periodic points of F in S. So it depends on what set that you work on. Sometimes it's infinite, sometimes finite, sometimes doesn't exist. So we call this periodic point of F for the set S. Now, if we want to include the other points before the periodic points, we say that that point is periodic. That means after a while, it's going to enter the cycle that map to itself again. So for this case, we call periodic point, or the other points that will not go back to a cycle that's going to be called wandering point. Now, for us number theories, we're going to pick a S that is quite meaningful for doing number theory. It could be the set of natural numbers, set of integers, rational numbers, or general finite fields. It could be function field as well, sometimes. So basically, the topic that we are discussing here is called Arithmetic Dynamics, which is a fusion of dynamical systems, number theory and algebraic geometry. We combine number theory and algebraic geometry, we call it just arithmetic geometry. So let's take a look at an example. If we have function c squared minus 29 over 16, let's play with 0, the initial point. This is periodic, which means at some time it's gonna enter a cycle, or basically you're gonna have finite forward orbit. All right. Now, if we try with the 0, we're gonna see fairly quick that it will not come back to itself, and the size of the numerator and denominator will grow to infinity. So for this case, we can just say that it's not periodic point, and most of the points are not periodic. Right. How about 1/4? If we try, you're gonna see that it's mapped to -7/4, and then -5/4, -1/4, -7/4. If you not go back to 1/4, but we can see that let's go back to -7/4. In this case, 1/4 is periodic point, and every point after that is called periodic point. All right, we can do a simple function like x squared minus 1, or even x squared, or x to the d for that matter. But this, we have that 1 is mapped to 0, 0 is mapped to -1, and then it's bounced back and forth between 0 and -1. And we're gonna call this case trivial in the sense that we can prove fairly easy that this would be all the points that we can have for periodic points. Oh, if we want to include infinity, it is possible as well, so that we don't have to, distinguish between the regular point and the point at infinity. And in general, for the being even, we can extend the case here to x to the d minus 1, and we're going to have the same structure. It's going to be a little less trivial here, but still, we can prove that this is going to be all of the periodic point that we can have for d being even. For d being odd, even if we change 1 to other rational numbers, we can prove that there's no point of period 2 or higher, because it's an increasing function. So at most, we're going to have just fixed point. So the function this form that we're going to discuss is there's a way that we can include the point at infinity so that we don't have to separate the case, and it's called recursive space. So basically, if points are scaled to the other point, we're going to treat them as the same point. So it's going to be more convenient to work on the recursive space here. And for the problems that we are interested in about the breakpoint and how it is bounded, one theorem that is very useful when we fix the function. If we fix a function, we have a theorem by Northcott in 1950 that for number field K, if we have morphism from projective space, and we call morphism. Basically, they are just polynomials function, but we work on dimension A. And if the degree of the morphism here is greater than 1 over k, then the set of pre-periodic points is finite. Note that this depends on the function phi. We have to fix function phi that we like, and then we can guarantee that the set of pre-periodic points is finite. Now, let's take a look at another set that is very interesting in terms of number theory, the elliptic curve. So if we have elliptic curve, say over a set of complex numbers, and if we extract only the x coordinate, right, x, y, we have two variables, right? And let's say we just take x, and then we look at the multiplication by 2 map on elliptic curve, and then we extract just the x coordinate, right? So that means we can have a corresponding map from projective space of dimension 1 to itself. So that's gonna be function. It turns out that this function has a explicit form. So we can rewrite this as a rational function of degree 4. And this is what we call lattice map. And we know quite a good deal about the case for point of finite orbit, or we call this torsion point, and form a subgroup of elliptic curve as well. Now, we can see that this type of equation, at least for elliptic curve, is equivalent to asking if we have a finite orbit or not, finite forward orbit. And we have a subgroup theorem, model weight theorem, that the given elliptic curve over Q, now we fix the field to be a set of rational numbers, is just the torsion subgroup with another point with infinite order. But of course, for us, we will focus on the point with finite order. So we're gonna look at the set T. This is the torsion subgroup. We have theorem by Messer in 1978 that this set can be described explicitly, and it is bounded, and at most the size of the set is 12, and we can extend this to the general number field as well, and this is called Morel theorem. So that means for the family of lattice map, we know quite a good deal about the upper bound, and doesn't depend on specific lattice map, and this is true for any lattice map, rational function of degree 4. And we have conjured by Morton and Zimmerman. It's called uniform boundedness conjecture in 1994, that this behavior should not be special only for the lattice map. It should be true for any rational function. In general, it should be true for any morphism over general objective space and over any number field. This is vastly unsolved, except for lattice map, of course. So this conjecture is very, very strong, because, for example, the case of rational field, and with just n equal to 1 for the degree of, I mean the n here is okay. Sorry for the typo. It's supposed to be capital N, which is the dimension of vector space, the projective space, and for the degree of the function, which is rational function here, is 4. So this covers the case of lattice map, and can just use this conjecture if it is there to imply the measure conjecture, at least for the upper bound. Right? And of course, for the general number field, we can use this to imply the Merle's theorem. Right? And of course, it look intimidating. So if we simplify to just the case of the field of rational number, basically, if we have rational functions with degree at least 2, the conjecture is that the set of periodic points should be bounded by just the constant, depending on the degree d of the function. And so it doesn't care about the form of the function, or it cares about is the degree of the function. Okay. Now, since then we have many results. For example, the recent one would be by Doyle and Punen in 2020, that if we fix a number field, and if we fix the length of the period, if we fix the length of the period first, now if we want to measure the length of the periodic point, it turns out that it is uniformly bounded. Okay, but when we fix the period first, okay, so it could be that we have infinitely many period. Okay, but if we give a period, let's say 3, then all the periodic points would be bounded. So this is very nice result, and we don't need to assume any conjecture, but this is true for only the case of unicritical map, or the explicit form is c to the d plus c. Right. Now, if we go back to the case of quadratic function, c squared plus c. So we know something about this. For example, if we look at the rational points of period 1, 2, and 3, we can have that there are infinitely many c that can produce the rational point of period 1, 2, 3. However, for greater period, for period 4 and 5, they will prove that we don't have such periodic points. We cannot find the primary c that produce points of period 4 and 5 by Morton in 1998, in Punen chapter for period 5, 1997. I think they were about the same time, just the times of publication that's different. And for period 6, still prove that we don't have period point period 6 as well, but here it is condition on Birch and Sweden-Dyer conjecture. So we have to assume this for the case of curve of Guinness form using this conjecture. Right. So that was in 2008, and since then there has not been any improvement. So it is still with period 6 and condition on the version Smith-Dyer conjecture. So it's still wide open, even in the case of x squared plus c. So the general step to think about is that we should generalize the problem. We kind of solve it. So let's look at the general form of unicritical map, which need to have one critical point, right? Integrity. The point and integrity equal to 0. That's just 1 point. Okay. So the general form is x to the d plus c. Now for the fixed point, it is relatively easy to solve by hand. For the case of odd degree, since it is increasing function, so it cannot have point of period 2, and you can solve for fixed point or point of period 1 easily. So the interesting case is when we have even degree, and we will just call x to d minus 1 here as the trivial case because it's easy to find the structure of critical point, and it's still interesting here. So for the case of 2 critical points, we're gonna call this case trivial when c equal to -1, and we have the structure of 2 critical point, 1 map to 0 and 0 map to -1, bounce back and forth. Of course, we can include the point at infinity as well. Now, the interesting case is when d equal to 4. When we have x to the 4 plus c, it turns out we can still produce infinitely many c that can have 2 critical points, 2 different critical points. This could be done by using something called a 2-Dynatomic polynomial, which is the way that you can mod out on the fixed point. Okay. You can generalize this to other period as well, but for us, we can just use this. And from this equation, we can transform to a simple looking unit curve y squared equal to x cubed minus 4. And we can use the fact that this unit curve has rank 1, that means it can produce infinitely many critical points. So we can produce a pair of the x and the c. For example, if we have c equal to this large number, negative 19,561 over 10,000, we can produce 2 critical points this way with its critical point as well. And this is the explicit form that we can produce the point of period 2 for x to the 4 plus c. And we can ask the same for x to the 6 plus c. It turns out we can change this to a hyperbolic curve y squared equal to x to the 5th plus 81. Okay. But still, the question is open for other degree d, okay, d being even here. Right? And we have a good theorem by us in 2015 that the form of critical point can be described in a certain way, at least for denominator. Now we're going to use his theorem just for the case of rational numbers, right? So that means this implies that if x over c is a rational critical point of x to d plus c, then the n here must be similar to the denominator of the c, okay, with the power of the d. So this gives us a description of denominator of critical point that must be related to the denominator of the parameter c here by the power of the d. Now, from this, if we use the two dynamic polynomial, we can rewrite the problem of period 2 using something called Fermat-Catalan equation. It is similar to Fermat equation, but we change from the power of x, y, z being equal to something else. But here the form that we have is x to the x1 to the k plus x to the k equal to delta c1 to the 2k minus 1, where delta here, if it is 1, then we call Fermat-Catalan equation, but we will abuse the definition of Fermat-Catalan equation a little bit by allow delta here to be 1 or 2.
Here you're taking 2 power, you're not taking, you're taking 2k minus 1, right? The power on the right side. In A.
Yes.
And B.
Okay.
Yes. Yeah. But if k is odd, the delta is guaranteed to be 1. Right? So that is the case when we consider on just period 2. Okay. Now we are moving toward the uniform boundedness conjecture. Okay, at least for x to the plus c. Now let's take a look at the conjecture that discuss this particular function x to the plus c. It was proposed by Hutz in 2015, and he called this generalized Punnett conjecture because Punnett made conjecture about x squared plus c. Then he changed from degree 2 to degree d. He conjectured that for the case of x to the plus c, the bound should be the same, that is 9. In fact, if we look purely with the degree greater than 2, the bound should be lower. So for the case of even degree, at least 4, then the set of periodic point should be less than or equal to 4. So this includes the point at infinity already. Right. Now, if we go back to the case of period 2, and for the degree, let's say 6, we can transform the two dynamic polynomial to y squared equal to x to the 5th plus 81. And Professor Emner was kind enough to solve this completely, that the solution must be in this form only, and then we translate it back to the parameter c and true periodic point. So we can have that for the case of degree 6. We don't have rational point of period 2, except when it's equal to -1, in which we call trivial case. Right. Now, for the general context of this problem of Fermat-Catalan equation, we're pointing out this form x to the p plus y to the p equal to c to the r. Okay. When we have that the degree of x and y are equal, then this is called Damon's program, and this is an attempt to refine the work of Andrew White to solve the Fermat-Catalan equation of this signature. Was done by, for example, Bennett, Kellenberg, Ngoc, Damon, Murrell, and Freitas, for example. Okay. And for this, we can use the result by Bennett, Russell, Yasani in 2004, that for C in this list from 1, 2, 3, 4, 1, 2, 3, 5, and up to 19. The definite equation x to the n plus y to the n equal to c times z cubed has no solution. So we can use this result and an example to guarantee that for the case of x to the 2k plus c, we can produce k with the property that 3 divides 2k minus 1 without any rational period point of exact period 2. This is not exhaustive because you can add some other results to have more degree that we don't have point of period 2, but shouldn't be complete for the result that we have. So we're gonna cheat a little bit here. Okay, so far we discussed up to degree 2, right? So degree 3, 4, 5 here, it seems like we don't have any result. We're gonna assume abc-Conjecture, and it state that if we have co-prime integers a plus b equal to c, well, we have to fix epsilon greater than 0 first, and this guarantee that they're going to be a constant k depends on the epsilon. That if we have equation in the form of a plus b equal to the c, then c must be less than the constant k that depends on the epsilon times the product of prime that we just take the different primes in the ABC. Okay, we discard all the power, right? And then for this we call radical of ABC. Okay. Now, if we don't have the exponent of 1 plus epsilon, let's say just 1, then we can produce a counterexample. So that's why we need the 1 plus epsilon here. Okay. Now, for this, we have a recent result. I gave a talk related to this problem in 2018, but since then, there are many results that have improved upon the unicritical polynomial and also polynomial in general. For example, Luber in 2021 proved that the case of unicritical map x to the d plus c can be uniformly bounded, not only over field of rational numbers, but over any number field. And in fact, she proved for the case of certain case of function field as well. But for that, she needs to use another version called abc-Conjecture, which means we can have a plus b plus c plus d, so on and so forth. And but she just thought like, okay, abcd should make sense in our way. So for this, we can have the bound. In fact, if d is greater than 4, we can still use abc-Conjecture. Only the case when d between 2 and 4 that you need to assume the abc-Conjecture that this is uniformly bounded. Now, recently she was manuscript on archive in 2021 that this should be true for any function as not any function, any polynomial as well. Okay. So that means for any polynomial of degree d, and if we assume the abc-Conjecture previously, then we can find constant b, that is the bound of the set of privilege points. So this is a very powerful result here, but again, we still need to assume the abc-Conjecture. Right. So the question is, even with the assumption of ABC or abc-Conjecture here, can we have quantitative result, can we actually find the explicit bound? And if we assume some more, it turns out that we can have an explicit bound. And the attempt was made by Baker in 2004. We had explicit version of abc-Conjecture. So if we let n be the radical of abc as usual, they're going to be absolute constant k, and doesn't depend on any epsilon at all. That the maximum value of abc from the equation a plus b equal to c here, less than k naught times n, log n to the omega over omega factorial, when omega is the total number of distinct primes that y here and c. And 2012, we had a very usable form by Lechuan, who is here, and Chari in 2012, when epsilon equal to 304. We can have that the c is less than the radical of abc to the power of 1 plus 3/4. And recently in 2019, we have refinement by Chim, Choi, and Sinha that the bound could be lower. So the maximum value of the ABC here is the minimum of n to the 1.72 or 10 times n to the 1/6, and 32 times n to the 1.6. So it depends on what you want to use at that time. So you pick one of the three here to be the minimum. And this is the version that we can use to refine the result. Okay. And the key lemma is for the Fermat-Catalan equation, the variant of Fermat-Catalan equation, x to the d plus y to the d equal to delta here, that we're gonna let it be something else, c to the d minus 1. The lemma under the assumption of abc-Conjecture is as follows. Basically, it's from the analysis of consecutive pre-predict points. Then we can transform to this equation, this arithmetic equation, x2 to the d minus x1 to the d equal to x3 minus x2 times z to the d minus 1, with additional condition on, being whole prime, let the maximum value be absolute value of x2, and the maximum value is greater than 1. But this, we can have that. There's no initial solution. So this is under the assumption of abc-Conjecture. We don't have integer solutions to this system. Now, if we assume further the explicit version of abc-Conjecture, then we can guarantee that the d is at least 10. So using this, we can improve upon the unicritical polynomial x to d plus c, that the case that we can have rational pre-predict point is only the trivial case. That is when the c equal to -1. Okay, so we can have only the only this case that can produce two big point and no more. And this proves the Hutch conjecture. Well, not proving, because this is still under the assumption of abc-Conjecture. And if we assume the explicit abc-Conjecture, we can quantify the bound that this is true for d being at least 7. We hope that it should be true for d equal to 6 as well, because for that case, this thing should happen from, for example, the experiment by Hutz. He calculate up to 10,000 that for the case of x to the 6 plus c, we should only have c equal to -1 that can produce a period 2. But this is what we have for now. So thank you.